Imagine looking up at the moon and realizing that something built on Earth has just struck its surface. On August 5, 2026, an abandoned SpaceX Falcon 9 upper stage collided with the moon after drifting through space following its original mission. There was no astronaut aboard, no one controlling it, and no warning visible from Earth. In a matter of seconds, a piece of human technology became part of the lunar landscape. But this was not simply a random accident. Behind the impact lies a story of orbital mechanics, gravity, and a rocket slowly changing its path through space. Stay with us, and subscribe, as we uncover exactly how it happened. To understand how this collision happened, we first need to understand the machine that eventually reached the moon. The Falcon 9 is a two-stage orbital rocket developed and operated by SpaceX. Its first stage provides the powerful thrust needed to leave Earth, while the second stage continues carrying the payload toward its intended orbit. After separation, the upper stage becomes an independent spacecraft-like object, carrying its own engine, propellant, guidance systems, and avionics. Normally, its journey ends according to a carefully planned trajectory. But in this case, the upper stage remained in space long after its original mission was complete. This particular Falcon 9 upper stage had a very different destination in mind when it launched. On January 15, 2025, the rocket carried Firefly Aerospace's Blue Ghost lunar lander and a Space Resilience lander toward the moon. After delivering its payloads onto their lunar transfer trajectories, the upper stage was left traveling through a highly elongated orbit around Earth. Instead of immediately returning through Earth's atmosphere, it continued crossing the region between Earth and the moon. Over the following months, astronomers tracked the object and refined its orbit. Eventually, those calculations revealed something extraordinary. Its path and the moon's path would intersect. Once the Falcon 9 upper stage had completed its primary job, it was no longer being actively guided toward the moon. Instead, it remained on a high-energy trajectory through the Earth-Moon system. In space, even a small difference in velocity or direction can produce enormous changes over time. The stage was also influenced by the gravity of Earth, the Moon, and the Sun. These forces continuously reshaped its path. What looked like a simple orbit was actually a complex gravitational dance. As astronomers continued observing the object, its future became clearer. This piece of hardware was not simply drifting aimlessly. Its orbit was gradually bringing it toward a meeting with the moon. The key to this unexpected journey was gravity. A spacecraft does not need an engine constantly pushing it to keep moving through space. Once it has enough velocity, gravity and inertia can carry it enormous distances. The Falcon 9 stage was moving within a gravitational environment dominated by Earth, but also influenced by the Moon and Sunday. As its orbit evolved, tiny changes accumulated until its future path became dramatically different from its original trajectory. This is why predicting the motion of an object around the moon is so difficult. A seemingly insignificant change can, months later, determine whether an object passes safely by, or collides with the lunar surface. For more than a year, the Falcon 9 upper stage remained an unusual object in the space between Earth and the Moon. Its journey began with the January 15, 2025 launch known as the Ghost Riders in the Sky mission, which sent Firefly's Blue Ghost and a Space Resilience toward the Moon. Once its work was finished, the upper stage continued along a high-energy trajectory. It was not simply falling toward the Moon in a straight line. Instead, its motion was shaped by gravity, orbital velocity, and the constantly changing geometry of the Earth-Moon system. Month after month, the stage moved closer to an encounter that had not been part of its original mission. At first glance, it might seem strange that a rocket launched from Earth did not simply fall back to Earth. But orbital mechanics does not work like a straight line. The upper stage had been given enough velocity to enter a trajectory that carried it far beyond low Earth orbit. Once there, Earth's gravity still controlled much of its motion, but the stage could exchange energy with the Moon's gravitational field as their paths evolved. The result was a complicated orbit that allowed the rocket to remain in space for an extended period. Eventually, the geometry became unfavorable. Instead of returning safely to Earth, the stage was placed on a trajectory that brought it toward the Moon. The danger did not appear as a sudden surprise. Astronomers had been monitoring the rocket stage and refining predictions of its future position. As more observations became available, researchers could calculate its orbit with greater precision. The critical realization was that the stage was heading toward a lunar encounter. But predicting an impact in deep space is extremely difficult. Small uncertainties in the rocket's position, velocity, and the gravitational environment can shift the predicted location by thousands of kilometers. Researchers therefore continued updating the trajectory as new observations arrived. Eventually, the calculations became strong enough to indicate that the Falcon 9 stage had a very high probability of striking the moon. As the final approach became clearer, the Falcon 9 stage was no longer just another object being tracked in space. Its predicted path was converging with the moon's surface. The estimated impact point was on the lunar far side, near the Einstein crater region, where direct observation from Earth is impossible. That made the event even more challenging to study. Scientists could predict when and where the collision should occur, but they could not simply watch it happen through an ordinary telescope. Instead, researchers had to rely on orbital calculations and spacecraft already operating around the moon. The countdown had effectively begun, even though the moon remained silent and distant. By early August 2026, the prediction had become clear. The Falcon 9 upper stage was on a collision course with the moon. Scientists estimated that impact would occur on August 5, near the moon's far side. There was no way to stop the object. With every passing hour, its trajectory brought it closer to the surface. The countdown was now unavoidable. On August 5, the Falcon 9 upper stage reached its final approach. Traveling at roughly 2.43 kilometers per second, the spacecraft slammed into the moon's far side at more than 8,700 kilometers per hour. The impact happened near the Einstein crater region, creating a fresh disturbance on terrain that had remained untouched for billions of years. In only moments, the rocket's long journey through space was over. The impact did not create a giant crater visible from Earth. Instead, the collision excavated lunar soil and rock, throwing debris outward across the surface. Because the moon has almost no atmosphere, there was no familiar mushroom-shaped smoke cloud. The material expanded through vacuum, following ballistic trajectories under weak lunar gravity. The impact site became a natural experiment. By studying the crater and surrounding debris, scientists can learn about the moon's shallow subsurface and how high-speed objects interact with ancient lunar terrain. The impact occurred on the moon's far side, making direct observation from Earth impossible. That is why spacecraft orbiting the moon became especially important. NASA's Lunar Reconnaissance Orbiter and South Korea's Danuri are among the spacecraft capable of studying the lunar surface from orbit. Their cameras can compare terrain before and after an impact, helping scientists identify changes that ground-based telescopes cannot see. For researchers, the crater is more than a mark on the moon. It is a new piece of evidence about the moon's surface and its violent history. The Falcon 9 upper stage hit the moon at roughly 2.43 kilometers per second. At that speed, enormous kinetic energy was released in an instant. The impact shattered the rocket and blasted lunar soil and rock outward, creating a fresh crater and ejecta field. Scientists can study these changes to understand both the collision and the moon's surface. The impact itself was not directly visible from Earth, but its aftermath could reveal the exact location. Scientists searched lunar images for a new crater matching the predicted impact site. Finding that crater would provide crucial evidence that the Falcon 9 stage had struck the moon exactly as orbital models predicted. It would also help researchers measure the impact's size and effects. The impact was not seen directly, but scientists soon found evidence that it had happened. Observations from Earth detected a faint debris plume containing sodium and lithium after the predicted impact time. The timing and location matched the Falcon 9's calculated trajectory. Together, these observations gave researchers strong confidence that the rocket stage had struck the moon exactly where expected. An impact crater is more than a scar on the lunar surface. The collision can expose material from beneath the surface, giving scientists clues about the moon's shallow geology. By studying the crater's shape, depth, and surrounding ejecta, researchers can estimate what lies beneath the surface and understand how lunar soil responds to high-speed impacts. This collision matters for another reason: the moon is becoming increasingly busy. Governments and private companies are planning more lunar missions, orbiters, landers, and eventually human activity. Every mission adds another object that must be carefully tracked. The Falcon 9 impact shows that hardware left in space can remain part of the Earth-Moon environment long after its original mission is over. Future lunar missions will need more than powerful rockets and advanced landers. They will also need careful management of objects left in lunar orbit and deep space. Tracking spacecraft after their missions end can help prevent unexpected encounters. As activity around the moon increases, understanding every object in the Earth-Moon system could become essential for protecting future spacecraft and astronauts. The Falcon 9 impact was not a threat to Earth, and it did not change the moon itself in any major way, but it revealed something important about the space around our nearest neighbor. Objects launched from Earth can remain in motion for years, following complicated paths that are difficult to predict perfectly. As lunar exploration expands, understanding those paths will become just as important as reaching the moon itself. A rocket launched from Earth, completed its mission, traveled through space, and ultimately became part of the moon. Its journey reminds us that space missions do not always end when the payload reaches its destination. Every object we send beyond Earth becomes part of a much larger cosmic environment. And as humanity prepares to return to the moon, the lesson is simple: exploring space also means learning how to navigate, track, and responsibly manage everything we leave behind.